Water freezes at 32 degrees Fahrenheit. That is not a complicated fact. Every child in America learns it in grade school. But in the winter of 1941, that simple fact was about to become the most dangerous engineering problem the United States military had ever faced. Because every engine in the American arsenal, every truck engine, every tank engine, every aircraft engine that used liquid cooling had water flowing through its block. And water, when it freezes, does something that almost no other substance on Earth does. It expands by 9%. 9% does not sound like much until you realize that the water is trapped inside a cast iron engine block surrounded by passages and jackets designed to contain liquid, not solid. When that liquid becomes a solid and swells by 9%, the cast iron does not bend, it does not stretch, it cracks. The block splits open like an egg, the cylinder head warps, the radiator bursts its seams, an engine that cost thousands of dollars and took weeks to build is destroyed in a single night by a substance that fell from the sky for free. This is not a story about cold weather. Cold weather is a setting. This is a story about a chemical, a company, and the industrial miracle that kept the engines of the American war machine alive in climates that should have killed them. The chemical is ethylene glycol. The company is Union Carbide. The product is Prestone. Let me take you back to the beginning, because the beginning is not where you think it is. Ethylene glycol was first synthesized in 1859 by a French chemist named Charles-Adolphe Wurtz. He was working in his laboratory in Paris, treating ethylene compounds with various reagents, and he produced a clear, colorless, syrupy liquid with a faintly sweet taste and no smell. He named it ethylene glycol because its molecular structure sat midway between ethyl alcohol and glycerin. He described its properties in a paper. And then nothing happened. For decades, Wurtz had created a chemical with no visible use. Nobody needed it, nobody wanted it. It sat in the catalog of known organic compounds like a word in a dictionary that nobody ever used in a sentence. The First World War changed that. Germany, cut off from global trade by the British naval blockade, was running short of glycerol, a critical ingredient in dynamite and other explosives. Glycerol came from animal fats, and the blockade had strangled the supply. German chemists scrambling for substitutes discovered that ethylene glycol could replace glycerol in certain explosive formulations. They synthesized it from ethylene dichloride on a small scale. It was a wartime expedient, not a commercial breakthrough, but it put ethylene glycol on the map. Chemists now knew it existed, knew how to make it, and knew it had at least one dangerous application. After the war, the chemical found its true calling. In the 1920s, as the automobile transformed American life, engineers confronted a problem that had plagued motorists since the first cars rattled down frozen roads. Water-cooled engines needed water in their cooling systems. In summer, water worked adequately, carrying heat away from the combustion chambers through a network of passages cast into the engine block and cylinder head, transferring it to a radiator where air flowing through copper fins dissipated the heat into the atmosphere. The system worked as long as the temperatures stayed above freezing. In winter, it became a liability that could destroy the engine overnight. The early solutions were crude and universally hated. The most common practice was to drain the radiator every evening when the temperature was expected to drop below freezing. This meant crawling under the car in the dark, fingers already numb, opening a petcock at the bottom of the radiator, catching the water in a pan, and then, in the morning, refilling the system with fresh water before attempting to start the engine. It was a miserable ritual performed millions of times every winter night across the northern United States. If you forgot, or if the temperature dropped unexpectedly, you woke up to a cracked block and a ruined engine. Repair shops in northern cities did a steady winter business replacing engine blocks that had been killed by a single frozen night. Some motorists added methanol or denatured ethanol to the water, which lowered the freezing point. Alcohol-based antifreeze was cheap and widely available, but it introduced problems that were arguably worse than the ones it solved. Alcohol is volatile. Methanol boils at 148 degrees Fahrenheit, far below the operating temperature of a hot engine. Ethanol boils at 173 degrees. In a hard-working engine on a warm day, the alcohol simply boiled off, leaving the driver with a system full of plain water that would freeze the next time the temperature dropped. Replenishing the alcohol was a constant chore. Worse, alcohol vapors are flammable. An engine running hot with an alcohol-based coolant was generating combustible vapors in the engine compartment, a situation that occasionally ended in fire. And the alcohol attacked the metals in the cooling system. It corroded the soft solder in radiator joints. It degraded rubber hoses. It pitted the water pump impeller. An engine running on alcohol antifreeze was slowly dissolving from the inside. Motorists who used it traded one set of winter problems for a year-round corrosion disaster. Ethylene glycol solved every one of those problems with the elegance of a molecule that seemed designed for the task. Its freezing point, when mixed with water, dropped dramatically. A 50-50 mix of ethylene glycol and water would not freeze until the temperature reached -34 degrees Fahrenheit. A 60-40 mix pushed the threshold down to -49 degrees. Those were temperatures that covered virtually every inhabited place on Earth. But the genius was not just in the freezing point. Ethylene glycol boiled at 387 degrees Fahrenheit in its pure form, far higher than water's 212 degrees. Mixed with water, it raised the boiling point of the coolant, meaning the engine could run hotter without the cooling system boiling over. This was critical for performance. A hotter running engine is a more efficient engine. Ethylene glycol expanded the operating envelope in both directions, protecting against freeze at the bottom and against boilover at the top. And unlike alcohol, it was not volatile. It did not evaporate out of the system. You put it in, and it stayed. A radiator filled with ethylene glycol coolant in October would still be full in March. The chemistry was, in the most literal sense, a permanent solution. In 1925, the Carbide and Carbon Chemicals Company, a subsidiary of the newly formed Union Carbide and Carbon Corporation, built the first large-scale ethylene glycol production plant at South Charleston, West Virginia. The location was not accidental. The Kanawha Valley of West Virginia was rich in natural gas, coal, oil, and salt brine. It had rail lines running east to the seaboard and the Kanawha River flowing west to the Ohio and ultimately the Mississippi. It had skilled chemical workers inherited from the salt and alkali industries that had operated in the valley since the 1800s. And it had something else that was essential: natural gas that contained ethane and propane, light hydrocarbons that were normally flared off at the wellhead and wasted. Union Carbide's engineers at their small experimental refinery near Clendenin, a few miles north, had developed an economical process for cracking these waste gases into ethylene, the basic building block from which ethylene glycol was made. The process went from ethylene to ethylene oxide through catalytic oxidation and from ethylene oxide to ethylene glycol through hydration with water. It was efficient, it was scalable, and it transformed what had been a waste product of the gas industry into the raw material for one of the most important chemicals of the 20th century. In 2021, the American Chemical Society recognized the Clendenin site with a National Historic Chemical Landmark plaque for founding the petrochemical industry. In 1927, Union Carbide introduced Prestone, the first commercially available ethylene glycol antifreeze. The name was marketing genius. Prestone, before the stone-cold freeze, before the engine cracks, before the radiator bursts. It came in a distinctive container, and it promised something that no previous antifreeze could deliver: year-round protection without the drawbacks of alcohol-based products. It was not flammable, it did not evaporate, it protected against both freezing and boiling. And in 1930, Union Carbide added corrosion inhibitors to the formula, chemicals that prevented the ethylene glycol from attacking the aluminum, copper, brass, and iron components of a cooling system. Prestone was now a complete solution. But the automotive market was the civilian story. The military story was about to begin, and it started not on the ground, but in the air. In the early 1930s, the American and British aviation industries were both struggling with the same engineering challenge: how to cool a high-performance aircraft engine without creating an enormous radiator that added drag and weight. Water-cooled inline engines, the type favored for high-speed fighters because of their narrow frontal area, needed radiators to dissipate heat. The radiator was essentially a large flat surface exposed to the airstream, and at 300 miles per hour, that surface created enormous aerodynamic drag. Engineers needed a coolant that could absorb more heat per unit volume than water, so they could use a smaller radiator. Ethylene glycol was the answer. Because it boils at a much higher temperature than water, it could carry heat away from the engine at elevated temperatures without vaporizing. The temperature differential between the hot coolant and the cold outside air was greater, which meant the radiator could transfer the same amount of heat through a smaller surface area. Less surface area meant less drag. Less drag meant more speed. The Curtiss Aircraft Company was among the first to adopt the technology. Designing the P-6 Hawk fighter for the U.S. Army in the late 1920s, Curtiss replaced the water coolant of earlier models with Prestone. The switch was dramatic. The radiator shrank by 1/3. The aircraft lost approximately 50 pounds of cooling system weight. For a fighter, 50 pounds was the difference between catching an enemy and watching him pull away. The Army's engineering division pushed the concept further, specifying a coolant operating temperature of 300 degrees Fahrenheit, far beyond what water could achieve without pressurization. The British followed, and the consequences were historic. Rolls-Royce, developing the engine that would become the Merlin, initially planned to use an evaporative cooling system with wing-mounted condensers. The system was complex and unreliable. When ethylene glycol from the United States became available in the mid-1930s, Rolls-Royce adopted it, switching to a conventional liquid cooling system with a compact glycol radiator. The decision was transformative. The Merlin's smaller radiator fit cleanly into the belly of the Supermarine Spitfire, contributing to the sleek aerodynamic form that gave the aircraft its extraordinary speed and agility. The Spitfire that won the Battle of Britain in 1940 owed part of its performance advantage to a chemical manufactured in the Kanawha Valley of West Virginia. There was a dangerous complication that early aviators discovered the hard way. Pure ethylene glycol is flammable. Early Merlin-powered aircraft, including the first Spitfire Mark I and Hurricane Mark I models that fought in the Battle of Britain, used 100% glycol as coolant. The header tank for the coolant sat directly at the front of the engine bay, behind the propeller hub. A hit from an incendiary round, or even a conventional bullet that punctured the coolant lines, could spray burning glycol into the engine bay and back into the cockpit. Fighter pilots in 1940 lived with the knowledge that a single well-placed bullet could turn their cooling system into a fire source. The sweet smell of glycol vapor in the cockpit was one of the most feared sensations in aerial combat. It did not mean the engine was about to overheat, it meant the coolant was leaking. And a leaking cooling system meant the engine would seize within minutes as it overheated without the fluid that carried heat away from the combustion chambers. The temperature gauge would climb steadily. The oil temperature would follow. The pilot had a narrow window, sometimes as little as 5 minutes, to either find a place to land or bail out before the engine locked solid. Rolls-Royce solved the flammability problem with the Merlin X by switching to a 70-30 water glycol mix run under pressure. The water reduced flammability dramatically. The pressurization raised the boiling point of the mixture to well above normal operating temperatures. Engine life improved. Oil leaks, which had plagued the early Merlin 1, 2, and 3 variants, decreased because the water glycol mix was less aggressive on seals and gaskets than pure glycol. This water glycol mixture became the standard for all subsequent Merlin variants, a formula that was adopted across the entire Allied liquid-cooled fighter fleet. The Merlin 12, which powered the Spitfire Mark II, was the first production version to use the pressurized water glycol system. Every subsequent Merlin, through the legendary 2-stage supercharged Merlin 61 that powered the Spitfire Mark IX and the Packard V1650 that powered the P-51 Mustang, used the same basic coolant system. The numbers were staggering. Over 168,000 Merlins were built during the war. Rolls-Royce factories in Derby, Crewe, and Glasgow produced them. Ford of Britain manufactured them in Manchester. Packard Motor Car Company built 55,000 in the United States. Every single one ran on ethylene glycol coolant. Every one needed a supply of the fluid for initial fill and for replenishment after maintenance, damage, or leaks. The logistical tale of a liquid-cooled Air Force extended all the way back to the chemical plants on the Kanawha River. The Allison V-1710, the American-designed liquid-cooled V-12 that powered the P-38 Lightning, the P-39 Airacobra, and early models of the P-40 Warhawk, also depended entirely on ethylene glycol coolant. The Allison was less celebrated than the Merlin, but was produced in greater numbers by a single manufacturer, over 70,000 units from the General Motors Allison division plant in Indianapolis. Like the Merlin, it would die in minutes if its coolant was lost. The entire liquid-cooled fighter fleet of the Allied Air Forces, American, British, and Soviet through Lend-Lease, depended on a chemical that had been a laboratory curiosity 60 years earlier. At high altitude, where outside air temperatures dropped to -60 degrees Fahrenheit, the ethylene glycol in the engine's cooling system kept flowing, kept transferring heat, kept the engine alive at conditions that would have frozen any water-based system solid within minutes of engine shutdown. Now bring this back to the ground. December 1941. The United States has entered the war. The Army is growing from a peacetime force of 1.5 million to an eventual strength of over 8 million. Every division needs trucks, lots of trucks. An American infantry division in 1944 was not a mass of men marching on foot like a Civil War regiment. It was a mechanized formation that included over 2,000 vehicles. Every armored unit needed tanks. Every tank needed support vehicles. Every truck and tank has a liquid-cooled engine, and every one of those engines needs antifreeze if it is going to survive a single night below freezing. The entire liquid-cooled fighter fleet of the Allied Air Forces, American, British, and Soviet through Lend-Lease, depended on a chemical that had been a laboratory curiosity 60 years earlier. Consider the mathematics of the problem, and you begin to grasp the scale. A standard 2.5-ton GMC CCKW truck, the six-wheeled backbone of American military logistics, the vehicle that carried everything from ammunition to rations to fuel to wounded soldiers, held approximately 4 gallons of coolant in its engine cooling system. The Army eventually fielded over 800,000 trucks of various types during the war. That is more than 3 million gallons of coolant just for the initial fill of the truck fleet, not counting replacement coolant for maintenance, combat damage, and the coolant that was lost every time a radiator hose blew or a water pump seal failed. A Sherman tank, with its Continental R975 radial engine or its later Ford GAA V8, held roughly 24 gallons of coolant. Over 49,000 Shermans were built. The Jeep, officially the Willys MB, had a smaller engine but still needed coolant. Over 600,000 Jeeps were produced. Add half-tracks, armored cars, ambulances, mobile generators, engineer equipment, bulldozers, cranes, and every other piece of military hardware with a liquid-cooled engine, and the total demand for antifreeze coolant was a number so large it required its own logistics category. And this was only the ground forces. The Army Air Forces needed ethylene glycol for every liquid-cooled aircraft engine. The Navy needed it for landing craft engines, destroyer auxiliary systems, submarine generators. The Coast Guard needed it. The Marines needed it. Even forces operating in tropical theaters needed coolant because the boil-over protection of ethylene glycol was as important in the jungles of New Guinea as the freeze protection was in the forests of Belgium. Union Carbide scaled. The South Charleston plant ran at capacity and beyond. Additional production lines were installed. Existing capacity was pushed past its rated limits. Since 1937, the company had maintained a monopoly on the direct oxidation process for producing ethylene oxide, the key intermediate chemical from which ethylene glycol was made. The process involved passing ethylene gas and oxygen over a silver catalyst at elevated temperature. The ethylene oxide that resulted was then reacted with water under controlled conditions to produce ethylene glycol. It was a multi-step chemical process that required precise temperature control, specialized catalysts, and experienced operators. Union Carbide had spent 15 years refining it. No other company in the world could match their efficiency or their scale. The Kanawha Valley plants ran around the clock, 3 shifts, 7 days a week. The complex at South Charleston sprawled along the riverbank, a landscape of distillation columns, pipe racks, storage tanks, and rail sidings. Steam plumes rose from cooling towers, the hiss of high-pressure gas lines mixed with the rumble of pumps and compressors. Workers on the production lines breathed air that carried the faint, sweet smell of glycol vapor, a smell that became so familiar to the people of South Charleston that they stopped noticing it. The chemical flowed from the reactors into storage, from storage into railroad tank cars, and from tank cars south to military depots in Virginia and the Carolinas, where it was repackaged into military specification containers and loaded onto ships bound for England, North Africa, and eventually France. By the peak of wartime production, Union Carbide was producing ethylene glycol at rates that would have seemed absurd to the handful of chemists who had worked in the original South Charleston laboratory 20 years earlier. The company also supplied ethylene, the basic feedstock from which glycol was made, to other chemical manufacturers. At one point, Union Carbide supplied 100% of the world's ethylene production. The Kanawha Valley had become the chemical center of the world, a concentration of industrial chemistry that rivaled the Ruhr in Germany and the chemical complexes of the Delaware Valley. South Charleston earned the nickname Chemical City. The strategic importance of antifreeze became fully visible in the European theater, starting with the first winter campaigns. The war in Europe was a winter war in ways that tend to get obscured by the summer imagery of D-Day and the liberation of Paris. The North African campaign of 1942 to 1943 tested the boil-over protection of ethylene glycol in desert heat, where daytime temperatures exceeded 120 degrees Fahrenheit and engines ran at the edge of their thermal limits. But it was the Italian campaign that first tested the freeze protection in European combat conditions. The Italian winter of 1943-1944 was savage. American forces fighting their way north from Salerno toward the Gustav Line, the German defensive position anchored on Monte Cassino, were operating in mountain terrain where temperatures dropped well below freezing at night and snow fell in quantities that buried roads and turned valleys into ice fields. Every vehicle in the theater needed antifreeze. Every medical evacuation ambulance grinding up a mountain road in the dark needed its coolant system intact. Every supply truck carrying ammunition to forward positions needed an engine that would start in the morning. The Italian campaign was the first sustained test of the American antifreeze supply chain in European winter conditions, and it revealed both the strengths of the system and the vulnerabilities. When coolant was available, the engines ran. When supply lines were disrupted by weather or enemy action, maintenance crews scrambled to protect exposed vehicles with whatever they had. The lessons learned in Italy informed the logistics planning for the invasion of France. The Normandy invasion in June 1944 put hundreds of thousands of vehicles on French soil, and by October, the first hard frosts were threatening every engine that sat idle overnight. The logistics planners had learned from Italy. Antifreeze was pre-positioned, supply depots were stocked. The system worked, mostly, until the Germans struck the Ardennes. The Battle of the Bulge was the ultimate trial. The German counteroffensive struck through the Ardennes forest on December 16, 1944, in the worst winter weather Europe had experienced in decades. At Bastogne, the temperature was 14 degrees Fahrenheit at 5:30 in the morning when the attack began. It got worse. Over the following weeks, temperatures dropped into the single digits and below zero in exposed positions. Blizzards swept the forest. Ice coated the roads so thickly that tanks lost traction on slopes. Fog blinded the air forces, grounding the fighter bombers that the American Army depended on for close support. And every vehicle in the American line, every truck, every tank, every ambulance, every jeep, every command car needed antifreeze to survive the night. Think about what a frozen engine means in that context. An armored unit that cannot start its tanks in the morning cannot defend its position. A supply convoy that cannot start its trucks cannot deliver ammunition to the troops at the front. A medical unit that cannot start its ambulances cannot evacuate the wounded who are dying of their injuries and of the cold. An engine without antifreeze protection that was left outside in Ardennes temperatures would be dead by dawn. Its block cracked, its radiators split open, its water pump housing shattered, its cylinder head warped beyond repair. Not damaged, destroyed. A mechanic cannot fix a cracked block in a field. The engine must be replaced, and replacement engines were hundreds of miles to the rear in depots that were themselves struggling to keep up with the demand of a battle that nobody had expected. The antifreeze held. It held because Union Carbide had expanded production to wartime levels that dwarfed anything the civilian market had ever demanded. It held because the military logistics system, despite its many failures, bottlenecks, and the chaos of a surprise German offensive, pushed sufficient quantities of coolant forward to the fighting units. It held because the chemistry was sound. A 50-50 mix of Prestone and water protected an engine to -34 degrees Fahrenheit. The Ardennes temperatures were brutal, among the worst conditions American soldiers had ever fought in, but they did not breach that threshold. The engines started, the trucks moved, the tanks rolled. The supply chain, strained to its limit but unbroken, kept the American Army fighting through the worst winter battle of the war. On the Eastern Front, the contrast was devastating and instructive. When Germany invaded the Soviet Union in June 1941, Operation Barbarossa was planned as a summer campaign that would crush the Red Army before the leaves turned. The Wehrmacht's logistics were designed for speed, not endurance. Their vehicles ran on water coolant with minimal or no antifreeze protection. Nobody had stockpiled ethylene glycol for a winter that was not supposed to happen. When the Russian winter arrived in November and December of 1941, and temperatures dropped to -20, -30, -40 degrees Fahrenheit across the vast Russian steppe, German engines froze solid by the thousands. It was not a gradual failure, it was a simultaneous catastrophe across the entire front. Crankcase oil, which at those temperatures had the consistency of coal tar, refused to flow. Transmission fluid congealed. Diesel fuel gelled. Batteries died. Recoil mechanisms on artillery pieces seized because the hydraulic fluid in the recoil cylinders had frozen solid. The guns could not absorb the shock of firing. German soldiers built fires under their tanks and trucks to thaw the engines, a desperate improvisation that sometimes worked and sometimes set the vehicle ablaze. Other soldiers left their engines idling all night, burning fuel they could not replace, rather than risk a frozen engine in the morning. The fuel consumption was ruinous. The German supply system, already overextended, collapsed under the combined weight of unexpected winter warfare and a frozen motor pool. The Wehrmacht's logistical failure in the winter of 1941-1942 was one of the turning points of the war, and the absence of adequate antifreeze was at the center of that failure. This was not because German chemistry was inferior. German chemists knew about ethylene glycol. IG Farben, the massive German chemical combine, was arguably the most sophisticated chemical manufacturer on Earth. They could have produced antifreeze in quantity, but the German military planning apparatus, obsessed with offensive speed and momentum, had assumed it would never need a winter logistics infrastructure for the Eastern Front. The assumption was wrong, and it killed tens of thousands of soldiers and destroyed tens of thousands of engines that Germany could not replace. The United States, by contrast, entered the war with a mature antifreeze technology and the industrial base to produce it at scale. This was not because American generals were more foresighted than German generals. It was because an American chemical company had been selling antifreeze to American motorists since 1927. 15 years of civilian demand had created the manufacturing infrastructure, the distribution networks, the chemical engineering expertise, and the supply chains that the military needed. The wartime military did not create the American antifreeze industry from scratch, the way it had to create the synthetic rubber industry or the atomic weapons complex. It inherited a working civilian industry and expanded it. The lesson applies to every American industrial miracle of the war. The capacity to build 50,000 tanks begins with the capacity to build 5 million cars. The capacity to produce millions of gallons of antifreeze begins with a yellow jug that civilian drivers buy in hardware stores every October. The military did not invent America's industrial base. It commandeered it and pushed it beyond anything its peacetime designers had imagined. The story extends beyond engines and radiators. Ethylene glycol found dozens of wartime applications that had nothing to do with keeping a block from cracking. It was a critical component of de-icing fluids sprayed on aircraft wings and propellers before takeoff in cold weather. Ice accumulation on a wing changes its aerodynamic profile, it adds weight, it disrupts the smooth airflow that generates lift. A bomber taking off from an English airfield on a freezing January morning with ice on its wings could stall and crash before it cleared the runway. De-icing fluid, a mixture containing ethylene glycol, was sprayed on the aircraft surfaces to melt existing ice and prevent new ice from forming during the critical minutes of takeoff and initial climb. The 8th Air Force, launching 1,000-bomber raids from bases across eastern England, consumed enormous quantities of de-icing fluid during the winter months. Ethylene glycol was also used in the manufacture of certain explosives, continuing the tradition that had begun in German laboratories during the First World War. It was an ingredient in some hydraulic fluids. It was a solvent and chemical intermediate in processes essential to munitions production. It was used in the production of synthetic fibers for parachutes and other military textiles. The versatility of the molecule, its ability to lower freezing points, raise boiling points, resist evaporation, dissolve into water in any proportion, and serve as a chemical building block for more complex compounds, made it one of the most indispensable industrial chemicals of the war. After the war, ethylene glycol's importance only grew. The same chemical that had protected military engines now protected the engines of the millions of cars and trucks that flooded American highways during the post-war boom. In 1962, the big three American automakers, General Motors, Ford, and Chrysler, began installing ethylene glycol antifreeze at the factory in every new car rolling off the assembly line. The decision was a recognition that antifreeze was not a seasonal specialty, but a year-round performance fluid. The higher boiling point protected against summer overheating as effectively as the lower freezing point protected against winter freeze. Prestone became a standard automotive fluid, as fundamental as motor oil or brake fluid. The yellow jug became an icon of American automotive culture, sitting on garage shelves and hardware store displays from Maine to California. But there is a darker footnote that must be acknowledged, because history does not allow us to celebrate industrial achievement without also accounting for its costs. Ethylene glycol is toxic. It tastes sweet, a molecular property that has nothing to do with sugar and everything to do with the way hydroxyl groups interact with taste receptors on the human tongue. That sweetness makes it dangerously attractive to children and animals who encounter it as a puddle on a garage floor or a spill from a leaking radiator. Ingested in sufficient quantity, ethylene glycol metabolizes in the liver into glycolic acid and then oxalic acid, which crystallizes in the kidneys and causes acute renal failure. The lethal dose for an adult human is approximately 100 milliliters, less than half a cup. Throughout its history, ethylene glycol has been the cause of accidental poisonings, tragic deaths of children and pets, and in several criminal cases, deliberate murder. The same chemical that saved engines in the Ardennes has killed family dogs who lapped up a sweet-tasting puddle in a driveway. Modern formulations include denatonium benzoate, a bittering agent so intensely unpleasant that a concentration of just a few parts per million makes the liquid taste revolting. It is a concession to the chemical's lethal double nature, a small molecular addendum to a 100-year history of both salvation and harm. Union Carbide itself grew into one of the largest chemical companies in the world, producing over 400 chemicals and plastics by the early 1960s, employing 12,000 people in West Virginia alone, and operating facilities across 38 countries. The company that had started with natural gas and antifreeze became a global conglomerate with its hands in everything from batteries to plastics to agricultural pesticides. And then came Bhopal. On the night of December 2, 1984, a gas leak at Union Carbide's pesticide plant in Bhopal, India, released approximately 40 tons of methyl isocyanate into the surrounding neighborhoods. The gas, denser than air, settled into the densely populated slums adjacent to the plant. Thousands died in their sleep. Tens of thousands more were permanently injured with damaged lungs, blinded eyes, and poisoned nervous systems. The exact death toll remains disputed, with estimates ranging from the company's figure of fewer than 4,000 to activist claims of over 15,000 immediate deaths and hundreds of thousands of lasting injuries. Bhopal became the defining industrial catastrophe of the 20th century. The company that had helped save the Allied war effort carried the stain of Bhopal for the rest of its corporate existence. In 2001, Dow Chemical acquired Union Carbide, absorbing both its assets and its liabilities, its patents and its lawsuits, its history of innovation, and its legacy of catastrophe. The Prestone brand was eventually sold separately and changed hands multiple times, but the product endures. Prestone Antifreeze is still sold today, still protecting engines, still bearing the name that was first printed on a can of ethylene glycol coolant in a warehouse in West Virginia in 1927. The story of antifreeze in the Second World War does not get told in the heroic register. There are no monuments to ethylene glycol. No museums display a can of Prestone beside the M1 Garand and the Norden bomb site. No veterans stand at podiums recalling the moment someone poured coolant into a Jeep's radiator and saved an engine from a Belgian winter. It is invisible history, the kind that hides inside the machines, inside the pipes and jackets and pumps that nobody looks at because they are covered by sheet metal and buried behind more dramatic components. It is a story of chemistry and logistics and the quiet industrial machinery that kept other machinery alive. But strip it away and watch what happens. Without antifreeze, every liquid-cooled engine in the European theater freezes on the first cold night of autumn. Without engines, the trucks stop. Without trucks, the ammunition does not reach the guns. Without ammunition, the guns fall silent. Without guns, the line breaks. The tanks do not roll. The ambulances do not move. The wounded freeze in ditches because the vehicle that was supposed to carry them to an aid station has a cracked block and a burst radiator. The entire architecture of mechanized warfare, the decisive advantage that allowed the United States to project power across two oceans and defeat the most formidable military machines in human history, depended at its most basic mechanical level on the presence of a clear, sweet, syrupy liquid flowing through the water jackets of 1,000,000 engines. Take away that liquid, and the army does not slow down. It stops completely. And an army that stops in winter, as the Germans learned outside Moscow and the Americans nearly learned in the Ardennes, is an army that dies. Charles-Adolphe Wurtz died in Paris in 1884, 43 years before the first can of Prestone was sold. He never saw the Kanawha Valley plants. He never heard the name Union Carbide. He never watched a Sherman tank grind through the snow outside Bastogne with its engine running at operating temperature because someone, somewhere in the supply chain, had ensured that the right fluid was in the right place at the right time. He synthesized a molecule and wrote a paper and moved on to the next experiment. That molecule kept the engines running. The engines kept the armies moving. The armies, eventually, won. And the clear, sweet liquid that made it all possible sits today on a shelf in your garage, in a yellow jug, waiting for winter, doing the same job it has done since 1927, keeping the cold from cracking open the machines that carry us through the world. Water freezes at 32 degrees. Prestone does not. In the winter of 1944, that was the difference between an army that moved and an army that froze, between victory and catastrophe, between a French chemist's forgotten experiment and the most destructive war in human history. The distance between those 2 points is measured not in miles, but in molecules, and the molecule that bridged the gap was ethylene glycol.